Hey guys, welcome back to my super fun tutorial lessons. Yay! So in this lesson, what I'm going to show you is how to write a simple VHDL program, and then use the University Waveform simulator that's built in to Quartus to check to see if that program is working appropriately. So the first thing we're going to do is I've already taken the liberty of creating a project and a directory, and I've called that inverter VHDL. And the first thing we're going to do is go over to File and click New, and here we're going to open up a VHDL file, and it's going to pop open a file over here in the editor window. And the first thing we're going to want to do is tell Quartus what library we want to work out of. And the most common library, so sometimes this happens where you type and things don't pop up. And so all you have to do is close this and don't save. And just go back to File and open again, and it should be fine. So we'll start with library. And there are several different libraries that are useful. So far, the only one that we've been using in our designs is the IEE library. It's just a common library. And so that's all I'm going to show you for right now. The next part we're going to want to add to this program is the entity block. And in the entity block, essentially, the entity declaration defines the name of the entity as well as includes a port list. And the port list are the inputs and outputs that we want that entity to have. So here I'm going to call my entity inverter. And this name is actually important because we'll have to later on give this file, our top level design, here, this file name, the same name as our entity in the program. Otherwise, it won't compile correctly. So our entity's name is inverter, and then we write is, and now we can begin our port list. We just type port parentheses, and here I'm gonna use I'm gonna do my inputs first, but it actually doesn't matter the order that you do these in. So you could put your outputs and your inputs in any order. And what's nice about these HDL languages is that in certain cases, unlike other programming languages like C++ and Python, sequence is not necessarily important. So here we've defined the name of our signal, which will be my input, and we do a colon. We'll define the mode, which will be an input, so in, and then we'll tell it what type we want it to take, and that's going to be standard logic. And always remember semicolons. And now I'll do my output, colon, out, standard logic. oops. Something to important note is we have to close this parentheses before we put the semicolon there. And then we'll go ahead and end it. Now the next part we're going to do is the architecture block. And the architecture block is very important. In the architecture block, we essentially tell we're telling the program what we want what function we want this entity, the inverter entity, to have. So normally, the beginning of the architecture block always takes this form. So we have architecture, then we have the architecture name, and I'm going to call it behavioral, which is kind of nice and descriptive. There's two different ways to do this here, but to describe the function of our entity, our circuit. And a common way to do that is using the behavioral method. And so this is I'm just using this as a way to easily describe what I'm doing, but you can write anything, any name here. It doesn't have to be behavioral. And so we're going to do architecture name of our entity name, inverter, is, and now you would normally do some sort of declaration. So you can do component declarations. So you'll tell before we begin the begin block what components we want the entity to have. So what components the inverter needs to have. But since this is a very simple circuit that we're trying to design and build here, it's we don't require any of those declarations, or any signal declarations as well. We could also define signals here. So we'll just go straight into the begin portion. So we just type begin, and then we include some statements about our inputs and outputs. And we'll just say that for an inverter, what we want is we want our output to be equal to the naught of our input. And with that, we are done. And essentially what this operator here does is it tells whatever signal is on the right, well, it tells whatever signal on signals on the left to have the value of the signal of on the right. So whatever signal is on the right will be assigned to the signal on the left, essentially. So let's make sure we have all the semicolons we need, which I did not. And I think that we're looking pretty good here. And now we can go ahead and compile and see what happens. And like I said, it's important to go ahead and name your file, your top level design entity for VHDL. We want that to be the same as our entity name, so we're going to call it inverter. And this should work just fine. We'll soon know if the analysis and synthesis continues past 4%, then we should be just fine and dandy. Looks like we're doing fine. So the next thing we'll do is, once this is done compiling, we'll come up here and we'll once again open a new file, and we'll go to University Program here, and we'll open that, and we can simulate our virtual circuit, I suppose you could say, and just see if it's working the way we expect. It's a good way to test it. And we can do the same exact thing using the program model sim Altera, which is included with the Quartus Prime Lite Edition download, and it's just a more powerful simulation tool. And you actually can, I'll make another tutorial showing how we can actually add and create text files like this in Model Sim, and just add them directly to the project there. And we're almost done here. Alright, looks like our compilation was successful. So what we'll do is we'll come up to File, New, scroll down to University Program, and the first thing we're going to want to do is go to Edit and Insert Node or Bus, and we'll go to the Node Finder. And here what we can do is we can just click List, and it should list all the inputs and outputs that you've included in your design. And we want all of these inputs and outputs, so we can go ahead and select both of them and click this button here, and it brings them over to our selected nodes. We also could just do them one by one. We just click OK, and they popped up here. And so we can do a few editing things to make things easier on us. We can go to set grid size, and I'm going to set the grid size to 1 microsecond, and I'm going to set the end time to 10 microseconds. And then also I'm going to select the input, and I'm going to go to value, and I'm going to go down to override clock. And so we can kind of control how this input's working, and go ahead and choose the period to be 1 microsecond. And with this, we should be ready to run. But one thing to check, we probably won't have this problem because the design is so simple. But we can go to simulation settings, and see if it's if the correct VHDL language is selected. Sometimes, even if you're running a VHDL program, selecting Verilog makes the simulator run. I'm not sure exactly why. It just seems kind of finicky. And then another option that if you run into errors, one thing that you might have had problems with, if we go into settings here, we go into simulation tab, make sure that the proper tool name is selected and the format for the output netlist is correct to whatever language you want. And then sometimes we go into more EDA netlist writer settings. If you're having errors, come here, check to see if generate functional simulation netlist, see if that is turned on, because a lot of times it's turned off if you don't set it up to be turned on, and that can result in some errors as well. So we'll go ahead and run the simulation. And so we can do that here, run functional simulation. Or we can go up to simulation and run functional simulation. Yes. And there we go. Here's our functional simulation. And for our inverter, we wanted our output to be the opposite of our input, and that's exactly what we see. So here, when the input is high, the output is low, and here when the input is high, the output is low, and we see that same exact pattern all the way down. It's exactly what we expected. So as you can see, the simulation tool here in Quartus is kind of useful. Not as powerful as Model Sim, doesn't give you as many options, but it's nice to check a few things with if you have a simple project or a simple design that you want to test, or even a more complicated one. But it's not as this is a little more intuitive than Model Sim, but Model Sim definitely gives you some more advanced features that are going to be useful, especially for us and the Helicity project. Alright, that's it for this video. In the next video, we'll do some discussion about the Model Sim software and how to use that and upload EDS files to that as well. Alright, thanks a lot.